Well, first of all, credits. This is not just a presentation from ProLabs, but from ProLabs and Mellanox. This work is a joint effort between the two companies. And it's a view into the future and the evolution of the optical transceivers that all of us use, whether we know it or not, in our networks, in our data centers, in our transport networks. And this is how a transceiver is done today, how it is built. It's a simple driver, a laser, and its data are transmitted on the optical side, and on the receive side, a photodiode and a transimpedance amplifier. Very, very simple. An SFP plus, it's designed like this. The thing is that the situation is changing, and it's changing a lot, because this simple model does not work anymore, will not work anymore. The more we try to squeeze bandwidth out of these interfaces, the more we try to push the speed, the more the problems. And people, you customers, you want to have things that are cheaper, smaller, and less power hungry, and we are really struggling to deliver that. Interfaces, electrical interfaces beyond 10 gigabits are really complicated, and copper is no longer a medium that simply propagates the signal. The signal is distorted, is attenuated. After a few centimeters, inches, the signal is completely degraded, and the processing ASICs, the DSP, even the microprocessor, the x86 microprocessors from Intel, they have an incredible capability of processing data, but the problem is getting data in and out of those chips. Still, a nightmare. And on the optical side, if we want to go at 20 gigabits per second per wavelength and beyond at a cheap, affordable price, again, it's feasible, but not economically practical. So how do we do it? How do we do it? We use our optics nemesis. We use electronics. Because electronics, for many reasons, I will mention a few of them later, but for many reasons, electronics had an incredible progress. Look, this is basically, let's call it performance. This is performance. From 1985 to 2012, almost 4 orders of magnitude. More than 4 orders of magnitude of progress. From 1995 to 2012, cost more than 1/100th of the cost per transistor. Optics, if we have to plot optics here, it's flat. It's basically flat on this scale. Electronics was impressive. We don't know it, but the Cray supercomputer of the 70s, which costed millions of dollars and required a couple of hundreds of kilowatts to work, was the Pentium first generation. Same kind of processing power. So how electronics help optics? Electronics dispersion compensation. This is a 10 gigabit signal at the receiver. Nobody can understand. There's no way to detect what's 1 and what's 0. And this is after compensation, done in electronics domain. Clear signal. This is 10 gigabit. But we are seeing the same things at 25 gigabits per second. What does it mean? It means that we do not have to push the design on the brute force way. We don't have to find ways to deliver that kind of signal. We deliver that kind of signal with cheap components, and this is what electronics understands. Few numbers. These are numbers from the International Solid State Circuit Conference, which is the most important event in this kind of space. Fairly stable technology, 45 nanometer, 32 nanometers. This is nothing that has yet to come. This is reality. Look at the numbers, 5.8 milliwatts for a 25 gigabit circuit capable of doing this kind of things. So this is a key building block that has been delivered. Forward error correction. I don't know how many of you are familiar with that. It's a technique widely used in the optical transport networks. You add a redundancy to the signal, and even if there are errors received, algorithms are able to detect these errors and correct them. It has been used up to a few years ago only on optical, very complicated, very high-end optical transport networks like the ones that ADVA described this morning. Because of cost, because of power. It was a technology which was not fit for transceivers because really it was impossible to integrate them. Now we are able, and these numbers are conservatives, we are able to do this in less than 200 milliwatts in very, very low power consumption, very low latency, and is of paramount importance for the next generation of optical interfaces that will go multi-level as we are trying to achieve. So do not transmit 0, 1. We transmit 0, a half, a quarter, a half, 3/4, 1. 4 levels means 2 bits per symbol. It means that we don't have to push the bandwidth. We use the processing capabilities of electronics. Very fast analog to digital converters. The signal is, this is what the receiver gets. It's not a 1 or 0, it's a number of levels. The receiver is able to understand what it is and map it to the right sequence of bits. Again, results presented this year, real circuits, not slideware, real circuits, with an incredibly low power and area occupation. Especially, this is very interesting, this last result. This is for coherent network, for OTU4 coherent network. It's an ADC that works with less than a watt, less than 700 milliwatts of power for a 100 gigabit coherent grade receiver. All these building blocks will change the architecture of the transceiver. We will not be talking about driver. We will say transmit IC because it will have the capability to compensate the copper. Will compensate distortion of the traces on the boards, on the switches. We'll have FEC encoding. We'll have advanced modulation and a bunch of features. We're not talking about laser. We are talking about transmit IC, and I will show you one of them in a few minutes. They will integrate optical circuits, not simply 1 and 0 transmitters. The same on the receiving side. We will have optical circuits inside of the device. And the receiver, the receiving IC will be a DSP, will be no longer a transimpedance amplifier to transform a photocurrent into a voltage signal. In the process, we will be able also to integrate all the control section that is needed anyway to make the machine work inside one of the devices. Because now, again, in terms of area and power consumption, there is no real reason why we can't do that. Why electronics was so successful? Well, it's this might be a simplistic way of representing it, but it's absolutely true. Optics has always been a very divided camp. Optics has always been about a bunch of technologies, a bunch of different devices, an incredible differentiation in the manufacturing processes that simply was not able to generate any economy of scale. Semiconductor industry kept that simple. Transistor, we replicate many transistors, we realize every function, but with the same building block. just one material, or almost one material, silicon, one dominant process, CMOS. And this means that you improve the performance, you lower the cost, you find application, you sell the application, money comes back to the industry, and over and over and over again. Optics, unfortunately, has not been able to replicate this model. So what we are trying to do is bring as much as possible of this semiconductor industry model, which enjoyed billions and billions of dollars of investment, into the optics industry. The killer application, the real market we are after, the data center. And there's lots of space in it because multimode interfaces, which are relatively cheap and has been widely used, are the first that are struggling to keep up with the evolution, because the reach of the multimode interface keeps on going backwards. At 1 gig, it was 550 meters. At 10 gig, you have to change fiber to get 300 meters. At 100 gig, with the same fiber of 10 gig, you get only 100 meters. And if you want to go just to 150, so just 50 meters more, you have to change fiber again, which is not something that people want to do. And data centers are becoming big, really just big. 150 meters is not enough. And the traffic inside the data center is much more than from the inside to the outside. It's about 3 orders of magnitude more, which is quite appreciable. Still, there are applications that have not yet unleashed their own potential. I was reading an article from General Electric, and they say that one of their jet engines delivers about 1 terabit of data per single flight, per engine. Multiply this per 2 engines per plane, per I don't know how many flights a day, and you get an incredible amount of data. And to process it, simply to move data from one server to the other, from one disk to another, from the disk to the processing unit, you need an interconnect network which has to be very efficient and affordable. So we need to push really the bandwidth in every dimension. We need to use everything we got. We need to increase the lane speed. We need to parallelize channels. And we need to use WDM, yeah, surprisingly, WDM into transceivers. This way, we're going to evolve the transceiver from SFP plus to QSFP to CDFP, which is the name that has been chosen for the 400 gigabit, and be able to design line cards with up to 10 terabit of processing power. The ICs are already going in that direction. Optics is following. Optics is what's holding the industry back. It's not the ICs. So, but in order to do that, we, of course, need to have a better integration of optics and electronics. We need to redefine the structure in terms of physical components of the transceiver to make it more simple, to make it cheaper and easy to manufacture. And this is what we are trying to do. So I will go fast. This is just a recap, because I want to spend a little bit more of time in describing you this device. So this is a 40G transceiver, transmitter and receiver. It's very simple, as you can see. There is a PCB which has the traces, the copper traces, and hosts the electrical components. Then we have two, which let me see, I know, not the pointer. Then we have the transmit IC, which is here, which is the, imagine it's like a component we mount on the PCB, but it's an optical circuit actually. We have the laser on it, an alignment mechanism, and the fiber that goes to, and the fiber goes out. Fiber goes in, receiver, a receiver circuit optical, electrical receiver. Behind this copper heatsink, and out to the electrical domain. Very few components. We have no TOSA, no ROSA, no optical subassembly, no gold boxes. It's not hermetic, which is very painful to build. It's much, much simpler. This is a schematic of the transmit IC. Here is the laser. It's passively aligned. No need to have in production machines that cost several $1 million to do active alignment of lasers, of lenses, isolators. The laser is put there and soldered. End of story. Light is coupled inside. Again, passive alignment. Split, 4 modulators, transmit out. Very simple, very effective. And the laser is a very simple device. It's like the one who's used for fiber to the home. We don't need very sophisticated devices with this structure to respond to the demands of the data center. Performance. When driven with a 3 volt, 60 gigahertz of bandwidth. With 1 volt, 36 gigahertz of bandwidth at minus 3 dB. So this point. And these are measures, these are not simulations. So it works just fine. I modulated at 25 gigabits per second with 5 dB of extinction ratio. IEEE for 10 gig LR demands 3.5 because that is 25, is a little bit, is more, but still more than enough for the data center reaches. Receiver, one nice thing, the structure is pretty much the same. So we do the receiver like we do the transmitter. The only difference is we have to put some germanium because the silicon is transparent at the wavelengths that are used for optical communication. So for the receiver, we don't need to be transparent. We use germanium to absorb light. Still, measure data. We're able to build a receiver up to 30 gigahertz of bandwidth. 30 gigahertz means 60 gigabit for an RZ transmission. Very efficient structure with simply a reflective structure to multiplex multiple wavelength into a single fiber. We can do WDM very, very easily. 100 gigabit base LR4, EEE 10 kilometer reach, and all the variants that IEEE is discussing for shorter reaches applications are based on multiple wavelengths. We have a very, very efficient way of doing it. Even to put more wavelengths, why limit us at 4? We can put even more wavelengths and build 200 gigabit, 300 gigabit, 400 gigabit transceivers with this kind of approach. At that point, we will be able to put the transceiver not plugged into our switches, but also inside for backplane communication, for communication between a CPU and memory. Because, again, the electrical bottleneck is not just on the faceplate of your system, it is also inside to make this subsystem communicate efficiently one to the other. Now we're putting an optical engine outside. 10 years from now, maybe less, we'll be putting optics inside the memory, inside the CPU, inside the network interface card, and all high-speed interconnects inside your networking equipment will be made in optical. And this technology will enable just a new breed of application. We hope to go to a point where electronics has to keep up with the bandwidth that optics has, which eventually will happen. And I'm afraid that many signal integrity engineers will need to learn new jobs because we will no longer need their help to make sure that we can drive 25 gigabits or 50 gigabits on copper. Maybe it's a long shot, but we want to look forward. And this module, we already have these modules. I mean, it's not rocket science. They are in Mellanox lab, and people are working on it. 5.2 milliwatts per gigabit. Without retiming, of course, with retiming it will be a little bit more, but 5 milliwatt per gigabit, it's really something. And these are the target reaches on multi-mode fiber, on single-mode fiber. 1550 nanometers. DWDM, transport world, and data center world coming together. Again, another simplification. So when this device is coupled with the board, when these devices become more and more intelligent, new applications can be delivered. These devices can, again, becoming intelligent, it means that they can contribute to OEM. They enable a bunch of new possible applications like link authentication. We have it's very easy to design an out-of-band communication system, since we are now designing silicon anyway, and adding a few hundreds of transistors, it's not a big deal, to handle a bunch of to handle some work that before was done by the software supervision, which is not very efficient if we can do it in the same way at transceiver level, offloading the CPUs from this painful back and forth and slow communication channel. Classic example. It's the simplest one, but it's not the only one. Regulate the performance based on the real link performance. If we have a lot of margin in terms of bit error rate, why not save some power consumption and reduce the transmit power, for example? Or we're using FEC. The chip can select between 2 or 3 different algorithms. If the most powerful one is not needed, why not use an algorithm with lower latency, if it's possible? If not, why? On the contrary, if we just have an algorithm with low latency but not enough correction capacity and the link is broken, we enable a more powerful algorithm and the link goes back up. So there are a bunch of things that are going on that will make sure that the transceiver will no longer be the dumb electro-optical converters that everybody uses but nobody likes. If we bring evolution to the transceiver, it means that replacing the transceiver with the next generation, we can bring features to the networking platform and protect the investment in the networking platform themselves. And transceiver will also become a pluggable ASIC that will help solve the electrical bottleneck that we have bringing data in and out of our system. Again, this is very nice, but if we don't work also and a lot on a better integration of optics and electronics to make sure that we really reduce cost by an order of magnitude, it will simply not happen. And this concludes my presentation.